Hello. Today we are going to explain about graph coloring problem, and the problem we have solved by using the following techniques: dynamic programming, backtracking, Welsh Powell, and we also done the visualization for dynamic programming and backtracking step by step, and also for the Welsh Powell we have showed the final output image. And coming into the details, these are our team members, myself Ravindra.
And myself Santosh Kumar.
Yeah, let's get into the objective that the project is about. This is the objective that we have worked on. Okay, let's get into the first one, dynamic programming. Well, here we consider an undirected graph with v vertices and m colors, and each color have an specific cost associated to that. And the main thing is like there should be no two vertices should have the same color, and we need to assign the cost of the color as low as possible. And before coloring the next vertex, we should check whether this is an adjacent to the initial node or the before node that is having, that is I mean the preceding vertex. And if it is having the edge, then we will not assign the same color, and then we will instead check with the another color with the lowest cost that is assigned to that. Yeah, and this is the input adjacency matrix that we are going to give, and the associated color matrix we are going to give. And here we are displaying the cost that is the cost of the graph that I have, the total coloring cost, and also the output final image for this technique algorithm. Let's get into a detailed demo for this. Yeah, as I mentioned, like this is the adjacency matrix that we have given, and this is the some random cost I have generally generated by default some static values. So let's color for that. Here we are just drawing the alert of the total cost that's this graph has taken is like 108, and this is the detailed step-by-step procedure output for the graph. As you see, the vertex 1 and 2 are adjacent to each other, so we are getting the different color to the second vertex. But for vertex 1 and 5, since it is unconnected or not an adjacent one to 1, so we have the same color, which is fine as for the dynamic programming. Yeah, let's go through another input matrix. Yeah, I have taken one other one. Yeah, let's color for this, and this is the total cost for this one. And as you see, this is the step-by-step visualization effect for the output. Yeah, this covers the dynamic programming and also the visualization for the dynamic programming. And this is the output that we have kept this random screenshot for that. Yeah, and the second one is backtracking. My friend Santosh will continue with this.
Hello everyone. Here our problem is about graph coloring by using a technique called as graph coloring. So in backtracking we have a graph which is undirected and we have k colors. So the main concept of the backtracking is recursively exploring the vertices, and if we have a feasible solution then it will go into that path, or else if there is no feasible solution it will discard this path. So basically I will explain it to you how it basically works. So here we have two graph coloring diagrams. The first diagram explains how the all the possible solutions if we are not using any adjacency vertex conditions. See, the first node has vertex RGB, we assign 3 colors, and it comes into the second node, it assigns 3 colors again. So there is a possibility that node 1 and node 2 can get the same color. But for the graph coloring problem, there is a condition that no two nodes should have the same color. So we will apply some backtracking technique. So here by using backtracking technique, we can see that vertex 1 has color red, and uh, it comes to the next vertex, it has all the 3 possible solutions. So it comes to the next vertex, it cannot assign the red color as it is an adjacent vertex. So it will discard that path, and it will come into the next possible color, which is green. So it colors the next vertex with green color. So similarly, in backtracking, as I mentioned, it checks all the adjacent vertices, and it explores if it explores only if it is an feasible solution, or else it will just discard the solution. And this is the implementation we have used. So here we are just inputting each vertex, adjacency matrix for the graph. If there is an edge, we will input the value 1, and if there is no edge, we are just simply inputting the value 0. Let's just go into the quick demo. Yeah, sorry about that. So let's input some details, colors. So I'm just giving a graph with simple graph with 4 vertices, and these are the inputs:
0 1 0 1 and 1 0 1 0 0 1 0 1 1 0 1 0.
and I am just giving the how many colors that are required for my graph. So it should be more than 3. Here I am simply giving the 3 color graphs, more than or equal to 3. So I am simply giving the 3 colors. It will generate all the possible solutions that are all the possible solutions using the backtracking. Here you can see we have generated some possible set of solutions by checking the adjacency conditions by using backtracking technique. So if we don't use any technique, we will get a large number of solutions which is not feasible for us. And now my teammate Ravindra will display the visualization technique for this backtracking.
Yeah. And as Santosh said, like there can be more than one possible solution. So what I'm doing is like here we are giving the input matrix. So what I'm trying to do is we are trying to display only one possible solution. So let's color for that. Yeah, as you see, this is a detailed step-by-step procedure for the backtracking as well. And we can also check this same, or we can try with the other input graph. Yeah, you can see this. Yeah, this is the detailed visualization for backtracking. So let's get into the final one, that is the
Let's see one more technique which we have implemented, that is graph coloring using Welsh Powell algorithm. So for many graph coloring problems, we must determine the number of colors. So that's one of the criteria, and most of the algorithms, like graph coloring algorithms, uses the greedy strategy, and in Welsh Powell algorithm there is a different approach. So initially the degree for each vertex will be calculated, and then all the degrees, all the vertices are sorted according to the descending order based on their degree. So the vertex with the lower degree will be on the first, and the vertex with the higher degree will be the last. So initially a color will be assigned to one degree, I mean one vertex with the lowest degree or the highest degree, and all the remaining vertices are traversed. If the no two vertices are connected, that means they are not adjacent to each other, then there will be they will be assigned colored with the same color if there is a possibility. And if two vertices are adjacent, then we will assign a new color for that one. So in the similar way, all the uncolored vertices will be traversed, and they will be traversed in the descending order of their degrees. That's the major criteria. Yeah. And we'll go through a simple demo. We will just send a adjacency matrix, and here we are displaying a final output. So we have implemented some few libraries, so we are using this here. Yeah, I can just simply give any vertex, like let's give the number of vertex before.
0,
Yeah, thanks Ravindra.
1,
Yeah.
0, 1, 1, 0, 1, 0, 0, 1, 0, 1, 1, 0, 1, 0.
Yeah, I have sent in all the inputs, so we will get it will generate a final image such that no two vertices will be adjacent to each other, and a new color will be assigned to the any uncolored vertex. Yeah, that's it. We have implemented these three algorithms.
Any doubts? Yeah, thank you.
Thank you.